Hello and welcome to this class where we were discussing about the formation constants of the metal complexes, and we see that if we can have more than one ligand system around the metal center, when we think of the corresponding hexaco species, that means if we have any metal ion which is bound by 6 water molecules and we allow it to react with some incoming ligand. So, we can have so many equilibrium constants. So, in case of copper, so far we have seen that the second K2 value we can get depending upon the individual concentration of the species what is forming over there. Similarly, we can have the third one, the K3 value and the fourth one. So, the fourth one we can write in this particular form simply or supposedly that you can have this particular formula in your hand. So, we should know about that it may not be stable form of this way. That means, if we can have the corresponding tetramine complex, actually that is forming over there as the tetramine copper species. So, your tetramine copper species will be stable one without these 2 water molecules, because we are thinking of that replacement of all 6 water molecules, but it is not actually taking place like this. So, you have this. So, what you can do for the determination of K4 value is only your formula is being changed. So, your concentration will also be different, and your starting concentration, that means when you have this, that means if we think that the presence of 3 water molecule and 3 ammonia molecules can be there, but when the fourth is coming, it will basically take away 3 such water molecules, that means these 2 will also go away. So, your water concentration will only be different from this particular part, and your ammonia molecule will be there. So, but these we are dividing, that means the formation constants of these complexes what we are talking about in a stepwise manner, that means the first, second, third, fourth, but it is not in actual practice. In actual practice, it is a concerted process where the overall reaction we have to follow. So, what is that overall formation constant? So, how we can think of a complete removal of all the water molecule by ammonia around this copper center. So, if we get that, for this particular beta 2, the formation of these by 2 of them, then if we can have 3 of them, then you have the beta 3, then you can have the fourth one. So, when the 4 of them can be there, that means K1, K2, K3 and K4. So, the product of all these 4, the individual stability constants can give rise to the product of all 4 K values, that means the K1 multiplied by K2 multiplied by K3 and K4 will give you a constant what is designated as a fourth step, overall fourth step of this will give you a beta 4 of this particular molecule. So, these equilibrium concentrations are also very much useful, because just now in our previous class what we are seeing that the corresponding hydrolysis and the salt formation, we are talking about the salt formation. So, how this salt formation can be useful to get you or take you in some point where we have seen in one case is the hydrolysis reaction, and how this particular salt formation or its hydrolysis altogether can say us something about its corresponding pH value. And if something is forming over there, that means some condition is forming for a particular reaction where we see that this particular pH is important in terms of not only the presence of only acid or only base, but a salt with acid or a salt with a base. So, this pH for the salt formation and the salt in presence of the excess acid or in presence of the excess base can give rise to a condition which we consider as a buffered solution. So, how we define this buffered solution, that we will see that this is a typical solution and a very interesting solution, because most of these analytical techniques, because in our next class we will be basically probably in this particular class also we will introduce the corresponding spectrochemical methods where we go for different titrimetric methods where we can use some instrument for the measurement of some titration reaction. So, this particular condition you have to maintain. So, before that we should know why we maintain or why we use some buffered solution, and is a typical process where the reaction is taking place for an acid base or the corresponding formation of the salt in presence of excess acid or an excess base. So, the definition tells us that it raises the pH, that means the pH is not very quickly changing when it is diluted with water and when acids or bases are added to it. So, this basically tells us that a favored type, that means a favored type of this particular conjugate acid base pair such as acetic acid sodium acetate or a corresponding base, ammonia is a base and the corresponding salt. So, the corresponding salt or the corresponding ammonium ion, which is the conjugate acid of that particular base. So, conjugate acid base pair, either acid and its corresponding conjugate form or the base or its conjugate form, can give rise to a corresponding condition where we get a buffered medium. So, a solution containing a weak acid or its conjugate base may be acidic, neutral or basic. So, how you think of? So, if by definition of this buffered solution, if we consider that depending upon the nature of the weak acid and its conjugate base, that means acetic acid and its corresponding salt, that means sodium acetate or potassium acetate, how do we know that that particular solution will be acidic, neutral or basic? So, that will be depending on the position of two competitive equilibria. So, just now what we are discussing in our previous class, that how the hydrolysis reaction is taking place and how the interaction can take place for this hydrolysis reaction when we consider that typical acid is reacting with water forming a corresponding ion, that means your water molecule is functioning as a base taking the H plus from the corresponding acid to give you H3O plus. So, this corresponding K value is for the concentration, individual concentration of H3O plus and A minus divided by the corresponding acid concentration. So, the second one, so this is basically the corresponding concentration what we just now see is corresponding acid concentration, which is termed as the Ka, that means A stands for acid. Acid is your Ha or HOAC, which is your acetic acid. So, the equilibrium constant for this K value is such that we are considering the corresponding acid of this concentration of the acetic acid. Now, if we can have for the corresponding conjugate base, that means the acetate ion which is getting hydrolyzed, we have considered that how hydrolysis can take place, giving rise now the corresponding Kb value, and this Kb value we have also considered earlier that this is nothing but your Kw and Ka. So, this Ka thing can come into the picture along with your Kw value. So, these all are related. So, Kb, Ka and Kw. So, we are considering basically two equilibrium conditions. The first equilibrium is lying somewhere and the second equilibrium how they are getting changed depending upon the nature of this acid and the corresponding conjugate base. So, if the first equilibrium lies further to the right than the second, the solution is acidic. Okay. So, this particular equilibrium, so what we have seen that the first equilibrium lies farther to the right, that means the corresponding dissociation of the corresponding acetic acid or any other acid. So, you have the corresponding acid form and its corresponding ions, the solution will be acidic. The second equilibrium, if it is more favorable, the solution will be basic. That means, if you can have this corresponding acetate ion which is reacting with water forming hydroxide ion. So, this is your corresponding strong base. So, if this equilibrium is favorable, you have a corresponding solution which will be basic in nature. Otherwise, if both of them are matching, that means this both of the equilibrium are competitive and of comparable magnitude, you can have a neutral solution. So, we can have the relative concentration of hydronium and hydroxide ions. So, one is for the acidic nature and another for the basic nature of the thing condition are dependent on this Ka value, and previously we have seen that this case is the Kb value, the Ka Kb and the ratio between the concentration of the acid and its conjugate base. So, concentration of the acid and its conjugate base, this means Ha and A minus, and the corresponding Ka and Kb value will tell us about the corresponding fate of the buffered medium. So, why we require this buffered condition? Because this buffered solution or the buffered condition is always a very much important thing. That means, this buffered solution we will use, we will afterwards we will see that whenever we go for some acid base titration or in some redox titration, we will see that we should not allow to change the corresponding pH of the medium to a large extent, because we will be doing this particular reaction in a very small pH window, where if we add this buffer solution, that means whenever we go for the titration using some acid or using some base or one oxidizing agent or reducing agent, the condition is such that we should not allow to change this particular reaction for its pH to a large extent. Otherwise, we will be in trouble if we just allow this particular window to be big enough. So, how this buffer can help in several areas? So, one such medicine we all know, the painkiller aspirin, we know that the 2-acetoxybenzoic acid, it contains buffered also to prevent the stomach irritation from the acidity of the carboxylic acid group in the aspirin. So, you have this corresponding acetoxybenzoic acid. So, benzoic acid is basically therefore a acidic form. So, if it is in the buffered medium, your acidity can be controlled in your body at the same time. So, these two things, that means your corresponding pH, control of the pH and the corresponding medium, how we are forming, that can be considered by a simple equation which is known as the Henderson-Hasselbalch equation. So, Henderson-Hasselbalch equation tells us that how we get a corresponding pH of a buffered medium. So, pH of a buffered medium can be obtained if we have a relationship like this from this equation, that pH will be related to the pK value plus the log of the corresponding salt and the acid, CNH divided by CHA. CNH is, if A is your acetate ion, it will be the concentration of the corresponding sodium acetate, and the CHA will be the corresponding concentration of the acetic acid. So, these two equations, this equation is basically useful to see where we consider the corresponding change in pH value with the change in the concentration of the reagent. So, when we change the corresponding reagent as your HCl, so if we just change the corresponding concentration from this, that means it is 10 to the power minus 3. So, when you change from say right hand side to the left, that means your concentration is increasing. So, your pH is also changing from say pH 5 to pH 1 and then to 0. But if you see the corresponding slope is almost is a 45 degree slope of this particular plot of this hydrochloric acid. So, as you move for the change in the concentration, its pH is changing in a very drastic manner. So, the pH dependence on the concentration of hydrochloric acid, which is unbuffered, that means no buffered condition has been added in terms of the corresponding salt of the hydrochloric acid. Similarly, if you can have some weak acid like HA, like your acetic acid, if it is unbuffered also, your pH can vary from 2 to 5 again due to the change in the corresponding concentration from 10 to the power minus 1 to 10 to the power minus 5. So, only in the dilute condition your pH is going to the corresponding pK value, which is 4.75 for acetic acid say. But if we see that a typical buffered medium, so the buffered medium you see is almost horizontal up to this point of 10 to the power minus 3 molar concentration of that particular mixture of acid and is salt. So, if it is acetic acid and sodium acetate mixture, and if it is buffered, we do not consider the corresponding change or the very fast change in pH value with the change in the concentration. So, that is why it is a very good advantage for handling a buffered solution for this particular reaction, or in some other cases the corresponding titrations. So, the effect of dilution for this particular plot we can explain in this fashion also. The dilution of the pH of a buffered and unbuffered solution, if we have a dissociation constant of this weak acid is 1 into 10 to the minus 4 molar and the solute concentration of 1 molar. So, 1 molar solute concentration if we consider, so due to the dilution from the left to right, what we see that for a particular dissociation of this HA and which is unbuffered in one case, how quickly they are changing from left to right following the Henderson-Hasselbalch equation. So, these buffers basically at some point it is not maintaining a pH at a constant value. So, what does it mean? That we are talking about some window or some space for that corresponding change in the pH value in the buffered medium. It is not that we can fix the pH at a particular value of say 4.5 or 4.8, but we get basically a range. So, a range of pH value can be there, where due to the addition of acid or due to the addition of base, this particular pH value will not change drastically. So, this do not maintain pH at a constant value, but change in pH is relatively small compared to your unbuffered condition. This change is relatively small. When small amount of acid and bases are added, you can consider the addition of base or addition of acid as the titrant. So, during the addition of those titrants into the reaction medium into the conical flux, your pH value will not change very much if your medium is a buffered medium. And a relative term related to that of your buffer capacity is also defined in terms of the number of moles of strong acid or strong base that 1 liter of buffer can absorb without changing pH by more than 1. So, some of these solutions, that means a solution of a buffered solution of 1 liter of that buffer can absorb a strong acid or the strong base. So, the corresponding value, the number, the digit for the corresponding number of moles of acid or moles of base which can be added to 1 liter of buffer such that your pH cannot change more than 1. So, plus minus 1. So, range that we are basically get for this particular ratio, because the Henderson-Hasselbalch equation is in the logarithmic value. So, the range is 1 to 10. So, the corresponding pH change will be plus minus 1. So, that particular range in terms of the corresponding moles values of these moles can be considered as your buffer capacity. So, this buffer capacity is also a very useful thing for our understanding for the different lakes in terms of acid rain, because this is a natural phenomena. We all know that due to the corresponding environmental pollution. So, we know that air pollution is there. So, this air pollution can give rise to several oxides of say sulfur, which is sulfur dioxide or sulfur trioxides, then corresponding NOx we call the different nitrogen oxides, and obviously carbon monoxide and carbon dioxide. So, if we have all these oxides in air and when rainwater is coming over all these oxides, these all will be converted to the corresponding acids. So, this we all know, then when it is coming through acid we get acid rain. So, our soil, the surface soil of our earth is getting polluted, or in the rainforest we get the typical acid rain, and is definitely the pH is in the range of 4 to 5 for this particular acid rain in some cases. So, what happened to that particular acid rain to some lake? Because if there are several lakes available and where we can have the corresponding rainwater accumulation within this particular lake. So, what should be the corresponding defense mechanism for this lake for a change in the pH? Because acid is supplied by in terms of the corresponding rain which is coming out due to the air pollution and is being dumped within the lake, and the natural mechanism is such that if we can have a corresponding buffer medium within the lake itself. That means, if your lake is forming and is surrounded by some of these limestone rock. So, limestone rock, that means calcium carbonate rock is there. So, if we can have calcium carbonate rock and this calcium carbonate in presence of your corresponding acid like carbonic acid H2CO3 or HCO3 minus. So, these are the things, that means you have the salt and the corresponding acid. So, this is the acid and the salt, and this combination of this calcium carbonate and its corresponding acid and its corresponding acid anions can give rise to a corresponding buffered condition. So, this buffered medium can take this acid from the acid rain, but its pH will not change very much because your medium is buffered. So, that is the natural defense mechanism or the natural process where we see that the different lakes can have a certain amount of buffer capacities, because we have the corresponding definition of this buffer capacity. So, how much acid or how much base it can absorb, but in this particular case it is the acid from the acid rate how much it can basically consume due to the formation of this particular deposition from these carbonate rocks. So, the principal buffer of natural water is basically a mixture of bicarbonate ion and the carbonic acid. So, the rocks are getting dissolving over there, and due to the availability of this acid either from the water itself or some amount of acid from the acid rain, we get the bicarbonate and the carbonic acid. So, the mixture of this bicarbonate and carbonic acid will be a typical buffered medium. So, that we will also see is a very good example for understanding this particular buffered medium when we talk in terms of the corresponding titration of this bicarbonate ion by some acids. So, that we will see also that how we can go for the corresponding reaction where we determine the analyte or the unknown analyte concentration following a titration, where the titrant concentration or the titrant volume will be useful to understand the unknown concentration. So, in this case the corresponding limestone rich area of those lakes, they have dissolved bicarbonates, and therefore, the bicarbonate ions and the carbonic acid. So, they have the corresponding affinity and thus low susceptibility to acidification, though rainwaters, the acidic rainwaters are dropping or accumulating inside the corresponding lake, but the buffer capacity of that particular lake will not allow its corresponding pH to change drastically from the corresponding acid rain what we get from there. So, just this particular part or at this particular point we will be finishing our equilibrium process. So, next we will be going for the spectrochemical method. So, today we will only just introduce that the spectrochemical method. How we can use that for our regular titrimetric methods or the titrimetric processes, where we consider this spectrochemical methods serially from the titration. We will introduce you for that titration reaction, how we go for the titration, and as we all know that the volumetric estimation is nothing but your titration. Volumetric estimation or the quantitative analysis of any unknown solution is your titration reaction. So, the chemistry which is involved in this particular titration, so we must have the corresponding chemistry involved in this titration reaction. What we can follow so far, what we are discussing is the corresponding equilibrium process. So, this particular equilibrium will also be there, and that equilibrium process, when we talk in terms of the corresponding acid base reaction or the hydrolysis of any other salt, we should consider the equilibrium and its pH changes. So, during the titration also we will consider a typical equilibrium for this acid base reaction and how the pH is changing and how to monitor, because you have to change the pH, you have to monitor the pH change, because at the neutralization point where we consider the corresponding acid base titration reaction. So, at the neutralization point your pH has a very characteristic value. If we consider that it is typically neutralized, so pH value should be close to that of our neutral value, as we all know it should be pH 7. So, this particular thing, that means there are several equilibrium processes will also be there. So, if we get this titration and if we see that this volumetric estimation, so this volume of some titrant, so some volume of our titrant we are adding, and during this particular addition of this titrant your pH is changing involving some of these equilibria. And if we consider that this particular plot, if we just simply plot something where in x axis we just plot the volume used for this titration, that means the volume of the titrant we are adding, and we are looking at the corresponding pH change. So, the other axis will be occupied by the change in the pH. So, for this plot, that whatever plot we will be getting in this fashion, that means the volume of the titrant what we are adding, and due to this addition of this titrant your pH will be changing. So, whatever we will be getting over here, so this plot basically will give us something which is known as your titration curves. So, these are nothing but your titration curves. So, how you start, where from we are starting, that means your pH can be starting from here say up to 10 or 11, or pH is starting from 0 to 1 at this particular point. And as you keep on changing the corresponding pH value with regard to the addition of volume of some titrant, that volume of this titrant addition can be your acid, it can be your base also. So, for this particular acid base titration, so you can have not only a single equilibrium, but you can have more than one equilibrium. So, assigning the different stages of these titration curves, that means assigning the different equilibria to the different parts of titration curves. This is important. How we assign a particular titration curve? Suppose your titration curve is like these, like this. Okay. So, what is happening over here, and what is happening over here, and what is happening over here. So, these are the typical assignments for this particular processes what is taking place during the corresponding neutralization reaction. So, how we can assign all these things? Then in terms of the corresponding pH, because the Henderson-Hasselbalch equation we have seen just now, that this has some relationship with the corresponding pKa value. The pKa values we all know that whenever we are considering the equilibrium of this particular processes, these K values are important. So, Ka and Kb values are there. So, if we are considering the corresponding acid dissociation constant, so we can have its corresponding pKa value. Suppose it is your acetic acid. So, acetic acid is being titrated with a corresponding solution of sodium hydroxide or potassium hydroxide whose strength is known. So, this pK value and the corresponding pK value what we will be requiring for a neutralization or the equivalence point. So, pK values and equivalent points. That means, if we get this particular titration curve where you see where is your equivalent point and how this particular pK value can be there depending upon its corresponding change in the pH value. So, related to this fashion, what we can find out in terms of the corresponding pK values, we can find out the use of indicators for this sort of titration. How we have to indicate this? That means, some indicators we will use from the school days. We all know that the different indicators we are using for identifying your acid base reaction. So, this acid base reaction is a very simple reaction where we can put some indicator and these indicators can change its color. So, color for acid form and color for your basic form will be different, and visually we can understand that which particular form is there. So, there will be change from one particular color to the other by these indicators. So, these indicators, what are of these the types, what are these materials. So, types of these indicators and which particular compounds, again we all know that the chemists always have this particular advantage for acid base, for redox, for complex symmetric titrations. In all these cases we will see that there will be different indicators to be utilized for this titration. So, for simple acid base titrations, how we can correlate this? We know some name only, say methyl orange, methyl red. These are the some name of these indicators for typical acid base reaction. How and where we can use these indicators? Where we can use MR or MO for the titration reaction. And interestingly, like that of our discussion related to the weak acid or weak base thing, that these indicators, the acid base indicators are also some weak acids. That means, they can itself take up proton or can donate that proton which is being accepted by these molecules, and due to that some structural change can take place and there will be a corresponding change in the corresponding absorption in the electromagnetic radiation. That is why it can give rise to or it can change its color. So, what we find over that you have a titrant solution and that titrant solution will be utilized. Then titrant solution of known concentration will be utilized with that of our reagent, which can be standardized. So, any acid or any base, some of these, that means we all know that, as I told you, that oxalic acid, which is a very good primary standard. So, your oxalic acid can be a standard solution and that standard solution can be stable enough and react with the analyte. So, this oxalic acid can be titrated with sodium hydroxide And when we titrate this particular oxalic acid with sodium hydroxide, we use some indicator and we titrate this with the analyte, and with a sufficient rate of the reaction we can reach up to the equivalence point, where the corresponding change in the color of this indicator will occur, and we can find out the corresponding amount of oxalic acid which is being consumed by this unknown concentration of sodium hydroxide. So, in this particular fashion we will find out the corresponding unknown concentration or unknown strength of the sodium hydroxide by the use of the corresponding oxalic acid, which is a known strength which can be taken in your burette for this titration. So, before going into the detail of the spectrochemical methods, where we will be utilizing the spectrometers or the colorimeters for this titration, in our next class we once again will discuss little bit about the different titrations, the titration curves and the back titrations, what are those things can be useful for our this analytical techniques. Okay. Thank you very much.